Hello, class. I wanted to talk to you about the teacher demonstration method, and I also am incorporating an experiment. That's why this is in the experimenting section. As we talked about in class today, teacher demonstration has multiple reasons, and y'all did a good job coming up with some of the reasons. One was if you're going over how to use a certain piece of equipment in the classroom, like a balance or a microscope, certainly that should be demonstrated before you just hand that out to the students. Another student, Wes, I believe, mentioned that teacher demonstrations are a good engage, get the students' attention, get them on task as soon as they come in the classroom, and that's true. I mean, a good demonstration can definitely get students listening and paying attention and doing what they're supposed to do. Other obvious reasons that you do a teacher demonstration would be, if you look at this right here, you have fire and you have glass. Definitely something you don't want elementary kids to have. Then the last reason that I can think of is the cost. These beakers are, I'm not gonna say they're super expensive, but if you're talking about enough beakers for a full class, yeah, they would cost a lot. But the fact is, you wouldn't let the kids have glass. So for the experiment, very simple. You know the answer somewhat. So the hypothesis is going to be is it a linear relationship? We're dealing with 1,000 milliliter, 400 milliliter, 250 milliliter, and I have some other beakers, but I don't have them at the house. But these are 3 beakers, and that's enough to determine whether the relationship between how long a candle stays lit and the beaker size, if it's a linear relationship. In other words, when we plot the data, is it going to be a straight line? You should use graph paper for something like this. Graph paper helps give you accuracy when you're setting up your increments. So we're going to see how accurate this is. We're going to look at it 3 ways: actual, sort of experimental data, math data, and graph. Graph data is a way of math, but we're also going to do some ratios to see how it works too. So we're going to start with the big one, and I'm going to try to hold it the same height. My clock keeper will tell me when to cover it.
Okay, hold on. Go.
One disadvantage of demonstration is if you have a lot of students and some are in the back of the room, they may not be able to see this very well. In fact, so I usually tell the students when the light goes out on this. Out.
23.48.
Okay, I actually tried this a while ago, and it was the same number. So 24 seconds. What I like to do now is kind of do a little math and graphing here. So if we plot this, that's going to be right here, 24 seconds. Come up 1,000. That's going to be our x. X goes right there for 1,000. So another thing you could do actually is guess how long the 400 is going to be, just with some simple ratios here. If you do 24 over 1,000 equals x over 400, that's going to be approximately 5 seconds, I think. How do you like how fast I did that math in my head? I actually punched this out earlier, so it's like 24 over 5. So we're predicting, let me do it this way, we've got predicted, we've got, which we're saying is 5 seconds, we've got actual over here. And so let's try the 400 milliliter and see if it's going to be 5 seconds. Hold it about the the same height when the clock keeper tells me to cover.
Okay. Wrong one. Okay. Go.
Out.
9 seconds.
9 seconds, okay. So we're off from the, between the actual and the predicted. That's the 400 milliliter, right?
Mm-hmm.
Yeah. So if we plot that number, I need a meter stick for this.
Do you need a ruler?
Or ruler, well, let's see, we go straight, eyeballing it. That's actually gonna put the 250 somewhere around the 5-second mark. If we have a linear relationship. Actually, it looks like it's more like a 6-second. If we connect these X, maybe 7 seconds, 6 to 7 seconds if we connect the, X's there, if it's a straight line. You could do more interpolation, I think is what it's called. You could actually use that number and see what 250 would be by setting up a proportion. Let's see, that would be 9 over 400 equals X over 250. That's 25 over 40 times 9. Do you know what that is?
Say it again.
25 over 40 times 9.
5.6.
So that's roughly, it's predicting it's going to be 6 seconds on this. So the predict is going to be 6. We were off on our first prediction. I'm going to say it's because that 1,000 number, for whatever reason, went out faster than it should have. But an experiment's an experiment. So. All right, so let's try the 250 now. You tell me when to put it covered up.
Go.
Out.
6.2.
6.2. That's a lot better that time. And that's actually about where it would show on the graph if it's a straight line. So, simple little experiment. You definitely can see that the amount of air in the beaker dictates how long the candle stays lit. There is a little bit of experimental error, but I want to tell you it's linear. I don't know why it wouldn't be linear, amount of air and how long it stays lit. So, good little experiments. Start your class if you're trying to teach experimenting. Thank you.